So in this video we're going to look at cumulative frequency diagrams, and we're going to take a histogram and develop it into a cumulative frequency diagram. Now first of all, let's understand what we mean by cumulative. So let's draw a set of axes, and I'm going to write on the y-axis, if you like, the horizontal axis, the months during which I'm going to save some money. So I'm going to go from January to May, and the amount of money I'm going to write on the y-axis, and I want to save, let's say, up to £100. See if I can save up to £100. So this would be £50 and so on. So how much do I save in January? Okay, well, let's say that I save just £20 in January. So let's draw it up to here. So in February, £10. In March, let's say I save £30, then £20 in April, £10 in May. Now that diagram does show me how much I save each month, but it's very difficult to see how much I save in total. So the idea of cumulative frequency, which is based on what we're doing here, is the same as cumulative anything. So it's cumulative money in this case. So let's write cumulative. It just means growing. So how do we grow our money? Well, the amount that we save in January is going to be brought forward to February. So we're going to add the amount for January in February's amount, and that will make this scale now cumulative. So adding January to February means we're going to add 20 to 10, which draws it up to here. And now for March, we have to add February's amount, so 30 add 30 brings it up to 60. Now that we've got 60, we add that to the 20 that we save in April. So in April, we have a total of 80. And the 80 we add to the amount we save in May, which is 10, bringing our total up to 90. So we've drawn our bars up now increasingly in a cumulative way, and that's the basic idea that we use for a cumulative frequency diagram. Okay, so let's just erase this diagram and instead have a look at a histogram. So a standard histogram based on a data set. And in this case, the data set that we're going to use is going to be based on the weight of 100 cats. We've used this example in previous videos, and so if you want to review the data set that we're working from, then go ahead and look at those previous videos if you haven't seen them already. Okay, so the weight in cats was calculated from 0 to 2, so we had an amount between 0 and £2, and there were none. Some cats were between 2 and 4, and so on, going up to 20. Okay. So that's numbered our x-axis, if you like, the horizontal axis. And now we need to fill in the data. So the data that we had gave us a histogram that looked like this. So there was just one cat that weighed between 2 and 4 pounds. And if we want to change this to a cumulative frequency, so cumulative frequency, okay, all we need to do then is add that 1 to this 4 here. So we've got 4 cats that weigh between 4 and 6 pounds, and that will give us 5 in this category rather than 4. So let's go ahead and do that. So bring it up to 5. There we go. We've got to do the same again to the 6 to 8 category. So add the 5 to the 18 here, bringing it up to 23. And then we add the 23 that we've got here to the, well, what is it, 60 here, giving us 83. Okay, and then we just have to add to to this column here, so this column to this column, bringing that up to here, and then add the 2 and 2 and 1 and 1 here. So let's go ahead and do that. So a cumulative frequency diagram always increases unless you're adding a negative amount, which is quite unusual. Okay, so there we are. We've got a cumulative frequency histogram showing the weight of our 100 cats, increasing until we get right to the top. And so the advantage of this is we can see how many cats we've got immediately. We just look at that last column and we can see it's out of 100 cats. What I want to do now is draw a line across here, tracing the shape of this curve. Now to do that, what I'm really saying is, say we take the 8 to 10 category here, I'm going to trace what happens in this category. So it starts here at 23, and then it increases as we go through the category until it gets to the end of the category, or class interval I should say, where we get to 83. So I want to draw a line always going from the right hand side of that bar, if you like, all the way through to the right hand side of the other bar, so sort of corner to corner. So whereas you might have with ordinary histograms traced a line, if you did trace a line from the middle, averaging the category, we're not doing that here because the numbers are increasing, and so we're always going from corner to corner, okay, until we get finally to this corner here, so that we get 100 cats right at the end here. So let's now draw that line through very carefully, okay, through those corners like that. Now this can be compared to the normal distribution. So the normal distribution won't any longer be a bell shape. It too will go up, and so a normal distribution curve is either this kind of shape, so an S shape, or we say an ogive or ogival shape, an S shape, and sometimes it would be steeper than the curve, sometimes it would be shallower. So generally speaking, when you've got a steep curve like this, it's going to come under. So let's draw in now the normal distribution curve. Okay, and so you can compare that now to the curve that we got from the cumulative frequency of our data set. Okay, so to be able to read these diagrams finally, you need to remove the histogram, so you no longer need these bars here, so let's just erase those. And then you can fit one or more lines onto the same graph, and you get a really nice comparison as you see these lines snaking through each other like this. Okay, now let's just erase the normal distribution and do something that you can't do with a standard histogram, which is work backwards towards the data. And what we're going to do is find some summary statistics that we can use to just summarize this kind of data set. We can only do this by working backwards from a cumulative frequency diagram. So the very first thing that we can see straight away is the number of cats here, so the total frequency here. So we've got 100 cats altogether, and we can also see then that there's a median value here, and the median is going to be the first statistic that we're going to write down. So let's just summarize this. So the summary is that we've got an estimated mean. It's going to be an estimate. Estimated, not mean, estimated median, which we can estimate from this point here. So this is going to be where we get the median value. So if we draw across from the 50 and then draw down, then we'll be able to see what the estimated median weight is going to be for 100 cats. Now, it won't be entirely accurate, but it should be within a few decimal places. So usually in exams you're asked to estimate the weight, in this case, of these cats. So estimated median, and you do that by drawing a cross. So let's do that now. Let's draw a cross from 50 until it intersects with the line. Now very carefully from the centre of that line, so from about here, if we draw down to the weight, we can see that the mean is between 8 and 10, and it's less than 9. So I'm going to say it's 8.8. Okay, so the estimated mean we can read off as 8.8 pounds. Okay, other summary statistics that you can list include the upper and lower quartiles. Now, what do we mean by that? Well, the upper quartile is halfway between the total and the median. So in other words, at 75 here. So if we draw a line from 75, so this is the upper quartile, and we draw down from the point of intersection with the curve, you can see again it's only going to be an estimate, but that the upper quartile, so we can just abbreviate that as UQ, the upper quartile then is going to be above 9, so I'm going to say that's 9.5. So we've got 9.5 pounds as the upper quartile. And what we're doing basically is finding out where the greatest probability is. So really looking at the centre of this distribution between the upper quartile and now the lower quartile. So let's draw in the lower quartile, which is at 25, so halfway between 50 and 0 at 25. And again, draw down very carefully from this point here. And I'm going to say that's 8.1. So the lower quartile with this example is 8.1. And finally, you might be asked for the interquartile range. So that's when we take the upper quartile and lower quartile and just subtract the one from the other. So we're looking at the range, the distance between these two. So the interquartile range, or IQR, in this case is 9.5 minus 8.1, which is 1.4. And again, pounds. Okay, so those are the summary statistics that are usually expected when we're analysing a cumulative frequency diagram like that. And hopefully you can see how we can work backwards from our cumulative frequency diagram once we've drawn it correctly to get those summary statistics. Okay, let's do another one. So this time what I want to do is use another example that we've used before, but this time of a histogram with unequal class intervals. So we had the example of an apple orchard, okay, and what we're doing here is we're estimating the number of trees in the apple orchard. So again, I'm going to label this cumulative. Now it's not cumulative at the moment because all I've done is given the standard histogram at the moment, so this would be ordinary frequency, but what we're aiming for is a cumulative frequency diagram. Now with the histogram that we have, where we have unequal class intervals, then we would have frequency density on this axis, which again isn't very helpful for reading off summary statistics. So I'm just going to use this histogram now to actually make a table, and then we'll erase this and end up with a line in exactly the same way that we did before. So let's now draw a t-table to get our frequencies from our histogram. Now what I'm going to do to take the data off here is I'm going to start by saying, well, what are the intervals? I'm going to list the frequency for each of those intervals. But when you're working towards a cumulative frequency diagram, you also want a third column adding up the cumulative frequencies. Okay, so let's start with the first interval. Well, that's 0 to, let's label up our x-axis first. So this is a percentage, so this would be 100%. So this must be 60, 40, 20 and 10. Okay, and this in fact is the percentage of trees. Percentage of trees that have good apples, so a percentage of trees. So we're going to write now the intervals onto our frequency diagram, frequency table. So we've got 0 to 10, so 0, so greater than 0, let's call it T, and less than or equal to 10. So from 10 to 20 now, 20 to, it jumps an interval, so we get from 20 to 40, then we get from 40 to 60, okay, and finally from 60 all the way to 100. Okay, so now we need to add the frequencies. Well, the frequency from in the 0 to 10 category is going to be 0. And what have we got here? Well, there's just 2 here. In fact, if I label this up, so again, we'll have 100 here. We have 50 here. And let's make sure this is easy to read. So I'm going to just number this. Whoops. In tens. So we get 90, 80, and so on. Okay. So what's the frequency from 10 to 20? Not the cumulative frequency yet, just the frequency. So we've got 2. So there are 2 in this 10 to 20% category that have 10 to 20% apples, I suppose. So 10 to 20 category is 2. Here we appear to have 12, but remember this would be frequency density, so we've got to multiply by 2, so it's the area of this. So in fact it's 12 times 2, which is 24. And here we have the same thing, so we've got 2 times 24, so 48. Finally, we have a reading of 6 on our frequency, but we have to multiply by 4, so this actually represents 4 times 6, which is 24 again. Okay, now to fill in the cumulative frequency. So I'm not this time going to add these together because that's rather a laborious way of doing it. I can simply now work with my table and just add the numbers together, add these values. So I start with 0, add the 2 to it, I will get 2, add the 24, this amount here, then by the end of the category I will have 26. If I then add 26 to 48, I will have 74 by the time I get to the end of this interval. And then finally, for this interval, I need to add this 24, so I get 98 apples in all. So that's the total number of apples, the total number of the total number of trees rather in our apple orchard. So there are 98 trees. So if I were to build this as a histogram, I would be building it right up to here to 98. However, I'm going to skip that stage now and just go straight for the line. So we need to transfer these values now onto our graph. So we've got 0, so between 0 and 10 we've got 0. So make a cross here or a dot. Between 10 and 20 we've got 2, so that's this point here. So far it follows the histogram, the standard histogram. At the end of this class interval, however, we've got 26, so I need to draw that up to 26 would be here. Get a little cross. Okay, at the end of the 40 to 60 interval, I've got 74, so that's going to go to here. Okay, and at the end of the final interval, we've got 98. So I'm going to draw my line up to just below the 100, so about here. Okay, so now let's get our red line and draw it nice and neatly through here. We haven't got as many points to go through here because of these unequal class intervals, but nevertheless we know roughly what we should be aiming at. So we can infer what happens to the line as we go through here, round here, and then finally to here. So it's going to tail off quite rapidly here. It's going to get down fairly straight through this point here, and then curves down and away at the bottom. So we're looking for this ogival shape. Okay, let's give it a go. And that looks pretty good. So we can erase these points here, go with that line. Okay, and finally let's remove now these this original histogram that we were working from. And if you're not given a histogram, of course you can just work straight from the frequency data in a frequency table like this, and that's very common. Okay, now for our summary statistics. So first of all, well, let's just compare to the normal distribution first of all. So let's just draw a normal distribution. And you can see it does look much more normal, in fact, than this one. It's very closely approximating, I would think, the normal distribution. But let's draw it on so we can just see that. Okay. And, okay, our summary statistics. So first of all, our estimated mean. Our estimated median. Now we need to be careful here, in fact, because our maximum is only 98. So rather than going across from 50, let's just remove that to start with. Rather than going across from 50, let's go across now from 49. So half of 98, 49 must be our median. Where it intersects, draw down carefully. So now we read off where it intersects with the horizontal axis here. And this is just under 50, so I'm going to say that's 40, let's say 48. So our estimated median rather, is 48, and it's measured in percentages, so 48%. Okay, so most of the trees have 48, or halfway through our data set anyway, we have 48% apples on our trees. Okay, let's now go for the upper quartile. So we need to, well, it's just below 75, isn't it? So it's 74.5. So 74.5, that's 70, that would be about here. And draw down. So we've got a reading now of our upper quartile is, I'm going to say that's 59. 59%. I think that's about as accurate as we can get it. Okay. Our lower quartile then, again just below the 25 mark, so about here. And that seems to hit exactly 40, so I'm going to say 40% is our estimate for the lower quartile. So our interquartile range 59 minus 40, nice and easy, 19%. Okay, so finally, what I want to do is look at box plots. So I'm going to move away, if you like, from cumulative frequency diagrams, but take this idea of the summary statistics and show those not this time on a cumulative frequency diagram, which is a little bit messy, but instead on this idea of a box plot. So what does a box plot look like and what does it do? Well, first of all, let's take then the data that we had for the first example, which was the 100 cats, and it was important to work out the median. We're not sure if this is exact. We could go back to the raw data to find that out. But we think the median is 8.8, so it's a good estimate. So we're taking 8.8 as the median. And we also looked at the lower quartile and upper quartile boundaries. And this defines the interquartile range. So we have the upper quartile boundary as 9.5 pounds and the lower quartile as 8.1. And that gives us, if you like, the spread, the middle 50% of the data where most of the probability lies. So most of the cats fall within that interquartile range between 8.1 and 9.5. Now, what a box plot does is it shows that very simply at a glance, and you can also put several box plots in the same area so that you can compare the different types of data. So first of all, let's draw a grid, and we need a scale at the bottom of our grid. And what we've got with a box plot is basically, well, think of it as an aerial view of a histogram or cumulative frequency diagram. So instead of looking at it side on this time, we're going to look at it from the top, as if we're looking down on the data, and that's what gives it its simplicity and the way that it shows the summary statistics very clearly. So to visualize this, it's a good idea to, if I just expand, if I sort of fold down the histogram from the center so you can see it. So that's where the histogram would be. And now if I fold it back up again, then we're going to draw a line this time representing the histogram in the center here. So we're not so interested, we're not at all interested, in fact, in the frequency. In fact, there's no, we've got no vertical axis at all. We've got no scale here. We've just got a scale along here, and that's so that we can, if we can press things like that, we can just concentrate on these summary statistics. Okay. So first of all, let's draw the median. So the very first thing we want to look at is the average values that we've got, and we're concentrating on the median. So the median is 8.8. So if I now draw my scale in, I want to draw my scale exactly the same really as I did for the histogram. So we've got 0 to 20. But our data, in fact, only starts at 2. So let's be aware that the data will only start here. The scale, though, is just a number line. So we're going to then put our box plot onto that scale, but it won't start until here, where the value is 2. Okay, let's just label up the axis. So we've got the weight of 100 cats in pounds. Okay, now we're ready to draw our median value. So if we go along our scale to 8, this would be 9, and then draw a vertical line. Like I say, there's no scale on the y-axis, if you like, here, so we can draw this any length that we like. Okay, so that's our median value of 8.8. Now what we haven't included is this maximum and minimum value here. Let's just is white. So I'm now going to record the maximum and minimum values here and here. And so we've got a minimum of 2 pounds and a maximum of £20. Now, of course, the cat that was in this category, the 18 to 20 category, probably didn't go up to the maximum, so we can't say that there was a cat that weighed 20, but it's possible that there was a cat that weighed 20, so that's where we get our maximum from. Again, the minimum range, we know that there were no cats between 0 and £2, so it's possible that the least that a cat could have weighed is this minimum value here of 2. Now these are the ends then of what we call the spread of data, and to indicate the spread we're going to just draw a line between the minimum and maximum values. Okay, so now we've got the average, the median, and we've got the spread of data between, in this case, 2 and 20. Finally, what we need to do is draw the box of the box plot. If these are the whiskers, then this is the box. So we're going to draw the box, which is going to represent the interquartile range. Now, we divide then the data up into quartiles, which is basically quarter values. We know that halfway, the median, is at this point here, and we know that the lower boundary for what we call the second quartile is at 8.1. So if we look at 8.1, that's going to be here. So this is the extreme of the lower boundary of the second quartile, and the upper boundary of the third quartile is going to be 9.5, so that's going to be here. So very narrow interquartile range for this particular data set. Okay, now we can draw a box. So the box, if you like, is picking out what's most important. The majority of the data is in this middle 50%, so that's where most of the probability lies. So if I draw a box here, that visually shows where most of the data is concentrated, and in the center of that here we have the median. So that completes the representation of this particular data set. That shows it very clearly on a box plot. Let's have a look now at another box plot, and this time interpret the data so that you can see how we can extract lots of really interesting information from box plots, which is often in exams or tests what we're asked to do. Okay, so this time what I'm going to do is show you a comparative box plot. And it's a comparative box plot of two diet clubs, because what we're measuring here is how much everybody has lost, how much weight has been lost. And the reason I'm doing this, the reason I've changed this quantity here to look at weight loss, is because it's a good example of a negative scale. So we have a 0 here, but we're going actually below 0 here to -1. And that's because it's possible that some people didn't lose weight, they might have gained weight, and we're just ending our scale here at -1 kilogram. Okay, so now let's do our interpretation. First of all, let's look at the average, the averages for each of our diet clubs. So first of all, we've got A. Now, the average we're using is the median, so let's read off from our weight loss scale the median for group A. And the median value is 1.7, so 1.7 kilograms is the median for group A. And the median for group B, by contrast, is only 1.2. So the first thing we can say is group A, on average, lost more than group B. Okay, so our conclusion is that group A, on average, let's just put on average, lost more weight. Okay, so it's important to show that you can not only record the values here, but also interpret the data. So let's now have a look at the spread. So average is important, the median is important, but we also need to look at the spread of data for any particular comparison. So the spread is indicated by the maximum and minimum values. So again, let's take those values off the box plot to start with. So the maximum, well, we'll start with the minimum. The minimum value for group A is 0.4. And it goes up to 3 kilograms. These are the least amount of weight that might have been lost to the maximum amount of weight. Whereas for group B, the least amount that might have been lost by somebody in this group is now down to here. So it would have been minus 0.6 kilograms, all the way up to the maximum that anybody lost would have been 2.5 kilograms. So what can we conclude from these two different spreads? Well, first of all, perhaps most importantly, we can say that everybody in this group lost weight. Okay, so everybody in group A lost weight. So well done to all of them. Whereas in group B, you can see we've got a negative. Now a negative weight loss must be a positive weight gain. So some people gained weight and some people lost. So some gained and some lost. So there's an interesting comparison between group A and group B in terms of the spread. Okay, finally, let's look at the interquartile range, and then we really have done a thorough comparison of both groups. Well, remember, the interquartile range is where most of the probability lies, so it's very important that we look at this and compare these two. Let's start with group A. So group A, if I measure the range now, we've got at our upper boundary, we've got 2.2, and we subtract the lower boundary, which is 1. So we've got an interquartile range for group A of 1.2 kilograms. If we look at the interquartile range for group B, we've got 1.6 at our upper boundary. So very different to the upper boundary for group A, but we can see, I think, visually that in fact they're going to be the same. So our lower boundary, so just to check that, our lower boundary is 0.6 kilograms, which is also 1.6, whoops, 1.6 minus 0.4. Okay. So in fact the visual check there was very useful. I could see that they were the same length, so I knew that my measurement must have been incorrect. So 1.6 minus 0.4 gives us 1.2 again kilograms. So again, our comparison here is that the IQR, so the majority of the data, falls in the same range, and that range is the same.